So we are very pleased to welcome Professor Petia Radeva from Barcelona today as our first plenary speaker. She is a full professor at the Computer Vision Center and Machine Learning at the University of Barcelona. Very accomplished researcher, belongs to 2% of best researchers in the world. A fellow since 2015, published many papers in top journals, about 100 papers, journal papers. Interested in pattern recognition, image processing with applications in food science and medical and medicine. And today she's going to talk about what to do when we need to classify fine-grained categories in presence of high uncertainty. So please welcome Professor Radeva. Floor is yours.
Thank you very much. First of all, I would like to say thank you for inviting me. This is really an honor to me to talk in this workshop. In fact, I should tell you that the S+SSPR was one of my first conferences, and then now going back to one of my first conferences is really especially very important to me. Let's talk a little bit about food recognition and all kinds of problems we can find, interesting challenges we can address using computer vision and machine learning, especially deep learning. Probably a lot of you have noticed that when you go to a restaurant, there is always somebody that is getting his or her smartphone and take a picture of their food. If you go to the Pinterest, for example, you will see that the second most popular category is related to food. Did you know that today there are more than 180 million of photos that are hashtagged as food on Instagram? And every minute we have 90 new photos that are hashtagged as food porn and uploaded to Instagram. And if we think who is doing this, 54% of this is done by young people, and 39% of young people posted it somewhere online. But people like me, we only 5% are doing this. Hopefully this going up, it's going more and more. So today we have a lot of images regarding food in internet, so we can find very nice data, and because of a lot of applications today, there is more and more interest in food image analysis. If you go and see in the computer vision and pattern recognition community, you can see that the number of food recognition papers exponentially augmented just last 10 years. So you see that there is more and more interest in food image analysis because this is really very complicated problem, and it in this way it allows to create and to address a very interesting computer vision problems. And also part of the popularity is due to very nice challenges. We have the iFood 2011. It was on fine-grained food categories, but now there are periodically running the AI crowd challenge for food segmentation, and also the large fine food AI that was organized on ICCV in 2021, and now is going again to be organized next year, and it has 1,000 fine-grained food categories and over 50,000 of images. So today there are very nice data sets. So if somebody has interested in these data sets, today you can find the food 256 with 256 classes, the food 101 that is one of the first data sets with 101 classes and 101,000 images, food X 251 and the food 1K with 1,000 of classes and 370,000 of images. Now, if we think in average, if this is enough, let's make some kind of parallelism. Today, in average, an average public food data set contains about 230 categories and 150,000 images. Of course, we can compare to the very well-known the ImageNet that has 1,400,000 of images and 1,000 categories. But if we want to address the food recognition problem, how many images and how many classes shall we consider? That is, our classifier should be able to recognize how many classes. If we go to the Wikipedia and ask how many food categories there are all over the world, according to the Wikipedia, we have 200,000 of categories. Do you know any classifier that is able to recognize 200,000 of categories? Me personally, I don't. And the question here is, if we need to train a classifier of 200,000 categories, how many images do we need in order to train such classifier? So definitely scalability is one of the very, very important problems for food recognition. But this is not only one challenge. If you look at this image, you will see here a lot of different food images. And if I ask you, what is this? Well, probably this is sushi, but also it could look like very much like some kind of sweet, some kind of dessert. If I ask you, what is this? Maybe this is carpaccio, but maybe this is also some kind of other meat, or even it could look very much like a tomato. And if we go to this, here we can see, for example, it could be like calamars, but also it could be like onions, fried onions, or some kind of sweets like donuts. So you see that for the food recognition, the big challenge is that we have a very close, very similar classes, so very inter-class similarity and very high intra-class variability. If you look at the all kind of tiramisu appearance, you will see it like a cake, like a mousse, in a very different way. And when we speak about very close, very similar classes, and this by definition is called as, known as fine-grained recognition problem. So here you can see different classes that are really appearing very, very similar. And now how to approach this fine-grained recognition problem? Here I prepared a few of our works and try to go very fast according to the time, to the limitation. So let's see, for example, how we approach the fine-grained food recognition problem. So as we mentioned, in the problem of the fine-grained food recognition is that we have some classes that are really looking very, very similar. It means that if we go and visualize in the feature space, some of the classes will be very, very close each other or even mixed. So what can we do? If we try to apply a general classifier with 1,000 of classes, we can see that this very generic classifier, it will be very difficult for this classifier to pay attention on especially on those classes that are very close each other. So in this case, what we did is we proposed to create several classifiers that are specialized on the subgroups of very similar classes. And in this designing different classifiers that are focused on subset of close classes, then we combine them in a multitask learning framework. So now the first question is how to discover this subset of very close classes. What we can do is we can use the confusion matrix of a generic classifier and use the confusion converted to a distance between classes. And if we define in this way the distance between classes, then we can apply a clustering method that is using the affine distance between classes in order to discover subset of similar classes. Okay, we did this, and here you can see, for example, how these three classes were discovered as a subset of similar classes, and they really look very, very similar. So when we apply this on the 1,000 classes on Food 1K, we discovered these 23 subsets of similar classes. And as expected, for example, all different tofus were put together. For example, here different chops and lambs were put together. For example, here different rice were put together. Different eggplants dishes were put together. Now, once we have these different classifiers that are devoted to the specific subsets of similar classes, now we put them in a multitask architecture. So in this multitask architecture, we have the first layers that are shared for all the classifiers. And because all of them, they are using the same domain, and it makes sense that this shared representation is allowing to generalize better the different classifiers. Then we embed the different classifiers and then the generic classifier using the 1K classes, the 1,000 of classes. And then once we have all these outputs that are the output of different classifiers, we connect them with a fully connected layer in order to get the final decision. So this fully connected layer is trying to take into account the decisions of the different classifiers. Let's see how this method worked. We apply this method on the 3 public data sets, FOOT101, FOOTX251, and FOOT1K, and we compare to the state of the art. And we use different backbones. Here we report 2 of the backbones, the transformer CSV enlarged, because this is one of the neural networks that is giving the best results in many, many applications. We also compared with the Volody5, and you can see that for the different data sets, the clustering discovered a different subset of classes. And then if we have for the baseline, we have some results of what we see here in this column. We see that in the 3 different public data sets, our design outperformed the baseline and the state of the art. And here you can see some images showing how the method worked. For example, if you have here in this picture, if the ground truth was egg roll, the baseline was saying bacon and eggs. In fact, bacon and eggs are very similar to egg roll, but are still different from the egg roll. And our design, our classifier, discovered it as egg roll. And it is the same with the, for example, for the egg roll, a spring roll was classified by the baseline, and our classifier guessed it correctly that it is egg roll. Or, for example, for tetrazzini, that was confused by the baseline as linguini. As mentioned, because this is fine-grained, even the baseline is, when it is confusing, it is still confusing with something very similar, but still the fine-grained design worked better. Okay, let's go back to the challenges of the food images. See, as we saw here, we have a lot of very different appearance and a lot of even ambiguity when we create this, when we annotate these images. Sometimes it is really very difficult to annotate correctly, and sometimes our data can have so much intra-class variability. So it is really, really very difficult to have a model that is very well working. If we try to visualize the loss function in such complicated problems is looking really very, very complicated, in a very irregular way. So here, for example, this is an example of 3 different loss functions that are for 3 different models that were trained on different data sets. This is from a paper from NIPS 2017, not on food images, but it is just an example. And my question here is, if we want to choose one of the loss functions, which of the loss functions do you prefer? The right, the central, or the left one? Maybe some of us will say, okay, we see here a very nice global minimum for the right function. But what happens here is that you see this is a really very locally positioned. So it means that if we begin from some point of the loss function here or here or here or here, it is very probably that we will be trapped in a local minimum, and it will be very difficult to come to the global minimum. In this case, you see that the global minimum of the loss function has much wider base. So it means that if we begin from all these points, we will probably come up, we will fall down to the global minimum. And this is something in the middle. So it means that in these loss functions, it's not only the question of which is the model that has the best performance, but also we are interested to know something more about the loss function. That is, we want to know something about the stability or the uncertainty of our model. Let's talk about uncertainty and how this could be helpful for us. So when we speak about uncertainty, we should know, and we know that uncertainty is coming due to different reasons. The uncertainty is coming because we have always noise in observations and annotations, because always we have high variability or randomness in the observation. We get our data from real world. I go to the internet and I get a lot of pictures of food images and food dishes. And all these data are messy or imperfect. And when we create our annotations in order to train our classifiers, we have human participation. Always when we have human participation, we always have some kind of error in these annotations. Our data have incomplete coverage of the domain. We will never have all the observations we need. And that's why we need to train and to use a training and validation and test a data set. And in statistics, a random sample refers to a collection of observations chosen from the domain without systematic bias. But in practice, we always have some bias. And we don't have any control over the sampling process. As I mentioned, we go to internet and we get our data. So we don't know who took the pictures, what device was used for the pictures, what are the geographic extensions of these pictures, what were the preferences of the people that were getting these pictures, etc., etc. Our models are imperfect. We never have 100% of performance. But at the same time, as George Box said, all models are wrong, but some are useful. That's why today we are applying deep learning algorithms in order to drive our cars. This doesn't apply just to the model, but to the whole procedure used to prepare it, including the choice and preparation of data, choice of training hyperparameters, and the interpretation of model predictions. And also, last but not least, our deep learning models are not able to say, sorry, I don't know. For example, if I train my model on these 8 fruit classes and I give a chocolate cake picture, it will never say, I don't know. It will, anyway, it will say that it is one of the trained classes. So this is an example of uncertainty of our model. Now, the question here is how to measure the uncertainty. There is one of the easiest and best, the simplest way to approximate the uncertainty is using a Monte Carlo dropout. So the Monte Carlo dropout is equivalent to performing k-stochastic forward passes through the network and averaging the results. And Gao and Gahramani showed that dropout at inference time gives an uncertainty estimator. So what we can do, if we apply at inference time several dropout and always the output is the same or very similar, in this case we can say that our model is very, very stable. But if all the time it is giving very different results, in this case we can say that our loss function has a lot of local minima. So what we can do is we can apply the Monte Carlo dropout and apply and then make the variance or mutual information or entropy of the output, and this it will give an approximation of the uncertainty of our model. And this is, in this case, it is the epistemic uncertainty of the model. Now, the question is not only to know if our model is more or less uncertain, but the question here is, how can I use this uncertainty in order to improve my model? And here I want to mention you very fast a few methods that we apply, how to apply the uncertainty in order to improve our model. For example, let us see how the uncertainty can be used for data augmentation. We know very well that all people that working in deep learning, we need a lot of thousands and thousands of data. So that's why we apply data augmentation. We can do classic data augmentation, or we can create synthetic images. But the question here is, how shall we do this data? How shall we do this data augmentation? Shall we use all the data? For example, let's see this example. Here we have two classes, the red and the blue. And then let us imagine we trained the classifier, and this classifier did its best. So still we have some errors. Like, for example, these blue points are on the side of the red points, and this red point is on the side of the blue points. Now, here we can say have some outliers, or we can have some hard samples that are difficult to be learned by our classifier, maybe because this subset are underrepresented in our data. So if I do data augmentation using all the data sets, because I have most of my data are here, so most probably the new synthetic data set could be in the same place. So it means that I will never help to these hard samples. Even I will make even more stable the classifier, and it will be even harder for my classifier to learn this data. Now, what we can do, we can try to look for these hard samples and focus on them. And we can give them priority to create the synthetic data to better represent the hard samples. So in this work, what we did is we used the epistemic uncertainty in order to discover these hard samples and make data augmentation focusing on these the hard samples. So if we get our data, estimate for them the epistemic uncertainty, and we want to focus on these data that have the highest epistemic uncertainty. So here our hypothesis is that our outliers that used to be a very small portion, they will be probably here on the right, but then they will be followed by our hard samples that are samples with high epistemic uncertainty. So we can use these samples in order to guide and to give them priority in order to create the data augmentation. And for this, we used GANs in order to create the new synthetic data, but much more guided by the data with the highest epistemic uncertainty. How did this method work? So let's see. Here we used different backbones. We used ResNet 50. We used some other VGG, etc. And we applied different data augmentations and data augmentation focusing on the highest epistemic uncertainty. So here you see that the accuracy improved when we were focused on the data with the highest epistemic uncertainty. But at the same time, also the epistemic uncertainty improved a little bit, but not so much as when we did the data augmentation, the classical data augmentation. Let's talk about the scalability. What we mentioned at the beginning is that scalability is one of the biggest problems of food recognition. So how to manage the scalability and how to use the uncertainty in order to help to the scalability problem. When we spoke about the whole number of food categories, we mentioned that there are 200,000 of categories. And we also mentioned that today there is no classifier working with 200,000 of categories. Now, do we really need a classifier of 200,000 of categories? Now, let us think practically. When we are visiting Mexico, for example, what is the probability to eat a food from Norway? No? Or when you are at this moment in Canada, what is the probability to eat food from South Africa, for example? Definitely, the probability is really very, very low. So what we can do is we can create a hierarchical classifier so that first we classify a cuisine, that is, we are trying to classify what is the cuisine in the image, and then we can apply a classifier that is focused on these dishes corresponding to this cuisine, instead of using a classifier that is classifying the 200,000 of categories. However, this has a problem. What problem do you think could be? The problem is that if we apply this classifier, and if we have an error of the cuisine, so if our classifier that is classifying the cuisine say that it is South African food, and this is wrong, it means that if it was really Canadian food, it will never recognize the Canadian food. That is called as error propagation. Okay. Now, what can we do in this case? In this case, what we can do is we can apply this hierarchical classifier only if we are very, very sure that the cuisine classifier is good enough. And in order to know if the classifier is good enough, we will impose several constraints. Okay, given an image, like if we apply a classifier and the classifier says that it is Canadian food, Canadian cuisine, and if we apply dropout and it still says it is Canadian cuisine, and if the classification of the Canadian cuisine is with the very low uncertainty, in this case we can trust this classifier and we can apply the classifier containing only Canadian dishes. But if these three constraints are not fulfilled, in this case we cannot trust to the cuisine classifier, and in this case it is better to apply the generic classifier. Let's see how this works. Here you can see some results. So if we apply a hierarchical classification without such constraints, in this case, you will see that due to the error propagation, the results are worse than if we apply the flat classifier. That is the classifier with all the classes. But if we apply the hierarchical with constraints, in this case, we can improve the flat classifier and improve the hierarchical classifier. And it is very important to apply the three constraints that were classification without dropout, classification with dropout, and the lowest epistemic uncertainty. If we use combination of two of them, we still don't have optimal solution. Okay. At the beginning, we mentioned that we have in Instagram millions and millions of photos of food, but that is having today food dishes is not a problem. What is really a problem to have food annotated dishes. Okay, so today our data sets, as we mentioned, contain up to 1,000 categories of annotated dishes, and we really want to have much to take benefit of the whole amount of or the much more data as we have in internet. So how to use this, how to leverage from the huge amount of non-annotated food images? As you can guess, in this case, we should speak about self-supervised learning. Today, that is last 5 years, I would say, there is big interest and a lot of attention on different self-supervised learning. And they are really getting very, very nice results in the bibliography. Today, we have the SimCM, the SimCLR, the Barlow-Twins, and many other methods that are doing self-supervised learning. Let us imagine, for example, the SimCM. It is one of the very good working methods. In this case, given an image, what the basic idea of self-supervised learning is, okay, if I have an image and then I classify it, that is, I apply a classifier, and if I distort this image, make some data augmentation, whatever, and I classify the distorted image, whatever the final solution is, it should be the same. Okay, that is because the content didn't change. It means that the original image and the distorted image should be classified in the same way. So in the SimCM architecture, usually given an image, okay, so in this image we have an encoder that is composite. We will see that architecture later, and then a predictor, and then we have the final solution. And if I have that distorted image and pass through the encoder, I want that the output of the predictor and the output of the encoder are classified in the same way. So if I have several images, okay, and their final representation, okay, that is represented by 2000 features, for example. So I want that the output of the predictor and the output of the encoder are the same. That is, if I make the cosine distance between these two representations, I want that this cosine similarity is very high. And this is for the first image, for the second image, for the third, for all images. Okay, so it means that the loss function will be sum of the cosine distance on all the images, the n images. And because we can have here symmetrically also, we can have the distorted image on the right, on the left, the original image on the right. So we can have these two terms that are representing the symmetric distances. Now, one of the question is that in the SimCM and SimCLR is that sometimes what can happen is that if the output of my predictor or my encoder it collapses to, for example, to the 0, so we will have the same distance, but in this case, this is not what we want. So an alternative to this has been proposed by the Barlow twins architecture that is not looking at the distance of the images, but is looking at the distance of the features. Okay, so if I have for the n images that are the images and they are distorted versions, so what the Barlow twins ask is that the first features are highly correlated, the second features are highly correlated, the third features are highly correlated, but there is very low correlation between the first feature and the second feature, the first feature and the third feature, etc., etc. Okay, so we want that the corresponding features are as much correlated as possible, and the different features are as less correlated as possible. What does it mean? Is that if I get for each image, I have the representations that are coming from both sides on the image. I have the projector, that is the encoder is giving this representation, and for the distorted image, I have this representation. Okay, so when I do the correlation between the corresponding features, I want that the corresponding features F1, F2, F3 are as high as possible. That is, the diagonal of this matrix should be as close as possible to 1. But I want that the correlation between different features of both representations is as low as possible. So it means that the Cij should be as close to 0. Okay. Now, what we found in the case of the food recognition is that in this case, what worked best is when we apply this on the negative pairs. So in this case, instead of comparing the features, what we were comparing the corresponding images the image and the distorted image. We want, in this case, the correlation to be as high as possible, and the correlation between the different images in the batch should be as low as possible. Okay, so if we do the correlation between the images and their distorted versions, so we want that image one is as high as correlated to the representation of the distorted image, but I want that the correlation between the first image and the second image is as low as possible. So in this case, we can create our correlation matrix where the diagonal corresponds to the correlation between the image and the distorted image, and the out of diagonal correspond to the correlation between the different images. Okay, it means that in this case we will have the diagonal will be of this form, and the out of diagonal will be the correlation between the different images. And we want that out of diagonal are as small as possible, and the diagonal elements are as close to 1 as possible. How this worked? You can see that here we applied and compared to the different models, to the Barlow twins, to the SimSiam model, and our method. And you will see that using just this representation and then applying this representation combined with the K and N, in this case, you will see that the classification was better in our proposal corresponding to SimSiam and Barlow twins. And if we use this representation and then apply, embed it in a classifier in order to improve the accuracy, so you will see that Barlow twins and SimSiam have given much worse results, and in our case, the SSL gave better results and smaller uncertainty, measured as variance, entropy, or mutual information. Okay. And the last question I would like to discuss with you is what to do when annotations are wrong? What to do when annotations are noisy? As we mentioned, the annotation of food is really complicated, and sometimes it is very difficult, and it is very easy to get wrong annotation, to say, okay, this is not an apple pie, but it is a streusel, for example. So in this case, we speak about learning with noisy labeling. And now the question here is, can we use uncertainty in some way in order to improve the learning with noisy labeling? And here I would like to mention that one of the best methods for us working in the bibliography, and this is called divide mix. In the divide mix, this is a very nice working method that is learning with noisy labeling. And basically here the idea is, okay, if I know that there are some noisy annotations, but I don't know which they are, I can make an hypothesis which are the clean and which are the noisy labels. I can treat the noisy labels as unlabeled and try to make my neural network to classify them in the best way as possible. So let us imagine we have a neural network, and this neural network has trained it already, and then I can look at the likelihood that I can look at the loss of my training data set. And I can see that some of the data will have a very low loss. So I can make an assumption that these are clean labels. And I have some other data that have high loss. And I can make the assumption that these are noisy labeled data. So we divide this with a mixture of Gaussians, with two Gaussians, separating the clean and the noisy labels. And then I can have two, that is one Siamese neural network that is composed by two neural networks, for which the first neural network, A, will keep its clean data and we'll try to analyze the noisy data of the other CMS neural network. And the same for the second component of the CMS neural network. For this also, I will get my clean data. I will use them as labeled data, and the second neural network will try to analyze the unclean, the noisy labeled data from the other neural network, treating them as unlabeled data. So it means that the loss function of each of these components will have one component that is coming from the clean data, another component that is coming from the noisy data that are treated as unlabeled data, and some regularization part of the loss. Now, in the bibliography, it has been shown, and there is a very nice improvement of the divide mix that is called contrast to divide. And this method just showed that if the Siamese neural network use a self-supervised learning component to pre-train networks A and B, the result could be additionally improved. Now, these methods are treating all the data and all the classes in the same way. However, learning is unbalanced across classes, and the accuracy of the model tends to vary significantly over different classes. So, we made a proposal to define dynamic weights based on uncertainty estimation in order to treat the different classes according to their uncertainty. That is, we are applying class conditional importance weighting by assigning large weights to classes for which the model has a poorer performance. It means that in our total loss function, the first loss term that is corresponding to the labeled data is as in the divide mix. But in the second part, where we try to classify the unlabeled data, we weight them dynamically by the uncertainty of the model to give higher priority to the more uncertain classes, trying to focus the model on these classes. Okay. How this method worked. Here we can see the results when we use divide mix, contrast to divide, and weighted based on the uncertainty, contrast to divide learning with noisy labeling. And here we used the different percentage of contamination of the data, introducing 20% of noise, 50% of noise, 80% of noise, and 90% of noise. And here is 40% of asymmetric noise. It means that here the noise is introduced by the closer classes. That is making even the process more difficult. So we did this here, for example, these are the results on CFAR10, but also it was very successful for the foot 101, for example, recognition. And here you can see that this is the best result and this is the average result. So in this method, improve it in almost all contamination rates, and the results are very nice. Now, just to finish, before finishing speaking about computer vision machine learning, I would like also to mention a few success stories. We are interested not only in developing new methods, but also using them and validating real situations and applying them in real problems. And I would like to mention a few of them. Here in the first one, this is in an European project where we created an app devoted to monitor the food intake of patients with kidney transplants. Because patients with kidney transplants, for them, the diet is very important before and after the operation in order to reduce the probability of rejection of the new organ. And this European project was successfully completed and developed by the Medical University of Groningen and Nestle from Switzerland. In the second European project, we applied these algorithms for food intake monitoring of elderly, because elderly people have problem with malnutrition. They used to use the same And in this way, they begin to miss some very important minerals and vitamins. And in the third European project, we applied our algorithms in a serious game, and that is called Green Habit. And in this case, this app is devoted to help people change their behavior and improve their healthy lifestyle. But probably for me, what is the best success is that one of my ex-PhD students 2 years ago created a spin-off that is devoted to exploitation of the food recognition algorithms. So this spin-off, this startup, today is already commercializing one API with food recognition algorithms that is already integrated in several apps. And on the other hand, also this company created a smart kiosk for self-catering restaurants. When you go to the self-catering restaurant and have the tray, instead of waiting so that the cash person make the list of the ticket for all the food in the tray, it is automatically recognized and the ticket is generated immediately. So in order to finish, as a conclusion, I would say that food analysis is a challenge and a trend for the CVPR community. And here you can see that there are many ways to work and to exploit these problems. And today we discussed it very short, the fine-grained recognition within a multitask learning framework. We also saw how to use uncertainty in order to augment data and improve the results using GANs. We also applied these methods for self-supervised robust recognition models, and these are also integrated in uncertainty-aware learning with noisy labeling. But still, we have a lot of open questions on food analysis. Still, we have big questions. What are the right models? How to improve them? How to use uncertainty in order to improve them? And this is really interesting, very challenging question to me and many other researchers. What are the right models? How can we make them more data-centric, data-specific? How to apply the self-supervised learning? How to apply fusion learning. That is, if I train my classifier on 100 classes or 1,000 classes, and tomorrow the smart kiosk needs to introduce new dishes, how to apply fusion learning in order to learn new dishes in the fastest way. And how to achieve scalability. This is really very, very open question. And from point of view of the data, also we have very interesting and underexplored questions, like how to manage ambiguity, how to manage error, how to manage noisy labels, noisy annotations, how to manage the big food data sets, how to avoid, how to treat the bias in the annotations. And also another question is how to use the knowledge behind the food data in order to make our classifiers much wiser and clearer and clever. That is, today people working on semantic knowledge are creating very nice food ontologies, but today still there are no any work trying to apply food ontology in order to analyze food images. Thank you very much for your attention.
Okay. Thank you very much for this delicious presentation, which made me already hungry. So time for questions and discussion, please.
You can say or you can write it out so I understand.
It reminds me of
comments.
Well, I just think it was a wonderful talk, but it gave me a deja vu about Chinese character recognition, which is also a problem with unbounded number of classes, and many of the problems that you raised apply, including mislabeling and so forth. And it may be worth taking another look at very large-scale historical Chinese character. Great. It was so well-rounded that you addressed most of the problems that came up. Thank you.
Thank you.
Question, please. It is known that basically biological objects, they characterized by high variance. This is known. And when you can have not only a few percent of outliers, you can have 30–40%. That can happen in the agriculture industry, for example. And then, for example, if you want to reduce the uncertainty, you apply consensus of classifier and try to make the certainty more certain when the classifier agreed all. But what actually happened if you focus on the difficult objects, only on those outliers, and then you do the data augmentation. You train your model on those examples, and then you have the test set with also very difficult examples, which has a very high variance. I mean, high variance if you have the ratio of the features in the same class, the highest value of the features, and the lower it can be 100. That's because I work in that industry. And so what will be your best strategy? Because you mentioned a few different algorithms and approaches for such kind of data.
Yeah, I completely agree. In fact, you see that, for example, in the data augmentation, we are focusing on the difficult samples that we call hard samples, right? So this is one of the approaches. When we apply the fine grain, we focus on the difficult classes. Yeah, but when we discover these subcategories, subsets of categories, we are focusing on the difficult classes. And when we apply the uncertainty as weighting, dynamic weighting, like for example in the learning with noisy labeling last method we discussed it. In this case, we are focusing on the difficult classes. So I completely agree that here the idea is how to treat the difficult situation, the difficult samples and the difficult classes, putting them more priority, making more data augmentation, looking for consensus. I also agree. In fact, I didn't mention because of the limitation of time, but Monte Carlo dropout is one of the ways to measure uncertainty. Even better way to measure the uncertainty is using deep ensembles, and also this is another method also we are working, and where the deep ensembles also are that is we are looking for this consensus of the deep ensembles, the different models of the deep ensemble in order to estimate uncertainty and focus on the data that have higher uncertainty. Yeah. So you see that all this data augmentation, weighting, focusing classifiers on difficult classes or difficult samples, all these are in this direction, right? Trying to put more emphasis on the difficult classes, but also taking into account that when we think about these difficult classes or difficult samples, especially difficult samples, maybe they are difficult because they are underrepresented, or maybe they are noisy annotated. So we really need to decide if we really want to insist to learn these difficult hard samples, but maybe we will do overfitting, or maybe they are wrongly annotated, and in this case, we should apply the learning with noisy labeling.
I agree, yes, with you, it can be the reason. First, and also there is a more difficult that the variation in different classes is different. That makes it even more complicated.
Yeah,
it's not the same.
Yeah, exactly. Yeah.
All right.
But I completely agree. This is, you know, a lot of still open questions and work to do. It's a very underexplored field to me. Yeah.
Any other questions? Okay.
Hi, Petia. Nice to see you again. My question goes, you showed mainly accuracy of your classification, but I can imagine plenty of applications where the global accuracy is not that important than false positives or false negatives. Imagine you have an allergy, okay, and you offer the wrong dish for you. That may be really bad experience.
Mm-hmm. Can you repeat the question?
Is, did you also consider the false positive rate, false negative rate? Okay.
The cost of the
the
cost of the
because it depends on the application.
The allergy also.
What you want to use it for.
Mm-hmm, mm-hmm. Yeah. In fact, here in this application, yeah, I agree. This is interesting to analyze. We didn't pay attention working in an asymmetric way, right? On the positive, the false positive, false negatives. This is something that, for example, for us was very important when we were working on medical images, because in there it is completely asymmetric problem. It is the cost of making a false positive of tumor, it's much higher than a false negative in medical context. Here we didn't do this yet, but definitely this is a very nice suggestion, and I think we should also look at this. I agree.
All right.
Thank you.
Okay, so I guess that completes our session and presentation. Thank you again. So the first paper in our session is a capsule network for hierarchical multi-label image classification. The talk is going to be given online by Khondaker, Tasrif, Noor.
Hello everyone, I'm Khondaker Tasrif Noor from Deccan University, Australia. So I'll be presenting my paper titled Capsule Network for Hierarchical Multi-Level Image Classification. So the content of this presentation includes a general introduction, motivation behind the work, a brief description of our proposed multi-level capsule network, followed by result and discussion, and finally the conclusion. So in order to introduce the topic, I would like to start by addressing what is the hierarchical classification. Hierarchical classification can be seen as a particular type of structured classification problem, where the output of the classification algorithm is defined over a class taxonomy. Generally, the classes are organized using a top to bottom or coarse to fine paradigm. And for this reason, it requires multi-level classification corresponding to the hierarchical levels. While performing classification, it is also require consistency among the levels. So it is also important to define what exactly is a class taxonomy. A class taxonomy can be defined as a hierarchical label tree, where the label tree generally follows a tree-like structure. The tree hierarchical structure follows taxonomy or a hierarchy in order to cluster the classes in multiple levels. This structure can be constructed by manually assigning the class level or using unsupervised learning approach. So here is a sample tree-like hierarchical structure presented for a CFR10 dataset. From top to bottom, the structure has three hierarchical levels. We address them as coarse, medium, and fine levels. For a hierarchical label tree, the number of classes gradually increase in the levels. Note that the coarse level has 2, the medium level has 7, and the fine level has 10 classes in them. Also, in a hierarchical label tree, all coarse classes is a superclass for all the medium classes clustered under, and medium classes is a superclass for fine classes clustered under. For example, medium class pet is a superclass for fine class cat and dog, where coarse class animal is a superclass for the medium classes bird, reptile, pet, and medium clustered under them. So hierarchical classification method requires to be implemented in a way that will always classify a leaf node or fine classes. Based on the literature review, existing hierarchical classification methods can be addressed as a flat classification approach, local classification or top-down approach, or global classifier or Big Bang approach. The flat classification approach generally represents multi-level classification models and typically predict only classes at the fine class or leaf nodes, ignoring the hierarchical structure in the dataset. However, it provides an indirect solution to the classification problem, and that is because when a fine class is assigned to an example, it can consider all its superclass are also assigned to the same example. Next, local classifier or top-down approach takes the hierarchy into account by using a local information perspective. And this approach, therefore, can be grouped based on how they use this local information and how the classifier are built around it. And there are the local classifier per node approach, local classifier per parent node approach, and local classifier per level. And lastly, global classifier or Big Bang approach are trained by considering the entire inter-class hierarchy at once. And generally, it treats all the level equally with equal priority. So a convolutional neural network, a CNN, uses convolution algorithm to extract feature in different layers in the network. And convolutional neural networks are traditionally designed to have sequential convolutional layers, where the shallow parts of the layer refer to the general feature, and deeper layer are dedicated to for more class-specific features. And using this feature, further, a branch convolutional neural network, or BCNN, was introduced, which links the network layer with the hierarchical level on the level tree, as top level consists of general feature and a deeper level hierarchy requires more class-specific features. The BCNN architecture uses a dedicated prediction layer for each level, taking input from the connected neurons in the network. This is an example of a global hierarchical classifier. And while training, the model considers all the hierarchical level in the dataset. And our proposed model applies capsule network per hierarchy for hierarchical classification. And our choice of capsule is motivated by their capacity to learn relational information. Capsule network uses a set of neurons to obtain feature and their transformation. So capsule network uses a set of neurons to obtain feature and their transformation, as also two capsules in different layers are connected and allowed to learn part-whole relationship. This enables the capsule to learn the hierarchical relationship between the object features. Additionally, capsules are equivariant in nature and have proven to identify objects from their translation. By forcing the model to learn the feature variant in a capsule, it is possible to recognize variants more efficiently with less training data. And thus, the capsule network has some advantages over the traditional models like CNNs. A neuron in a capsule network contains the likelihood as well as the properties of the features and output a vector. For example, the face neuron outputs a vector which may contains likelihood, orientation, size, etc., as mentioned in LO and S. With this structural information, capsule can detect the inconsistency in the orientation and size among the object feature and therefore output a much appropriate activation for the object class classification problem. And equivariance is the detection of objects that can transform to each other. And a capsule network shares the same capsule to detect multiple variants in the same network. For example, if the face image is rotated by 30 degrees, the capsule will generate a vector which will have the same magnitude but different orientation. So, which is unlike in a traditional neural network, a capsule network detects whether the face is rotated or not, rather than realize that the faces match a variant that is rotated. Capsules in different layers are connected, as shown in the figure below, where the output of the secondary capsule layer is calculated based on the relation with the capsule in the previous layer, as presented in the equation. In the equation, a Cij is a coupling coefficient and updates its weight based on the iterative routing algorithm. Using an iterative routing process, each active capsule will choose a capsule in above to be its parent capsule. So here I present our proposed neural architecture for multi-level capsule network. The network has a dedicated capsule layer and prediction layer per hierarchical level and have a common reconstruction part. In the figure, a secondary capsule in different colors represent different levels in a hierarchical level tree, and thus it can have as many of the hierarchical levels exist in a level tree. Please note that in the architecture, there is a common input and feature extraction block, which takes input and the extract local features and pass them to the primary capsule in order to form the primary capsule. The output from the primary capsule goes into the next capsule layer in the different hierarchical level. And thus, the secondary capsule layer for different hierarchical level shares a common primary capsule. And this capsule layer provides a vector output for class prediction, utilizes a dynamic routing algorithm, which considers the agreement between the feature properties in capsule layers. And furthermore, each level has its own prediction layer, which estimates class probabilities by making use of a logit function. And lastly, the network uses an auxiliary decoder network to reconstruct the input instant because our proposed model utilized the reconstruction loss while training the model. This is executed by combining the decoder output for each hierarchical level into a final one by concatenation, and as demonstrated in the diagram. So in order to train the overall capsule network, we have employed a loss function, which is a weighted summation of all class prediction loss and the overall reconstruction loss. In the overall loss function equation, tau is the reconstruction loss weight, while LR is the reconstruction loss, lambda n is the weight for hierarchical level, and Ln is the class prediction loss, where n is represent the hierarchical level and capital N is the total number of hierarchical levels in a data set. Well, for the reconstruction loss, we calculate it using L2 normalization, where X is the input instant and X hat is the reconstructed input instance. And for class prediction loss, we have applied a hinge loss function where Tn values is 1 if the class is present, or else it is 0, where Vk is the output vector from the secondary capsule, and K is the class level, where gamma, M plus, and M minus were hyperparameters, and the values were defined according to our experiments. And now we turn our attention to the result for all the models under consideration. And in order to train and validate the models, we have considered 4 different data sets. And there are MNIST, Fashion MNIST, CIFAR10, and CIFAR100. And please note that MNIST, Fashion MNIST, and CIFAR10 dataset provides fine level classes, and CIFAR100 datasets provide medium and fine classes. So we have followed the footstep of some pre-established hierarchical level trees for this dataset, and which are cited here. In the hierarchical level tree, MNIST have coarse and fine levels only, and for Fashion MNIST, CIFAR10, and CIFAR100 dataset, we have used coarse, medium, and fine levels. So in the level tree presented here, K is the number of classes present in each levels. And furthermore, we have considered some established classification model in order to compare our hierarchical capsule network. So in order to do that, we have chosen a branch convolutional neuron and a classical capsule network. And branch convolutional neural network approach employs convolutional neural network based architecture, and it reflects the tree structure and considers all the levels present in the level tree. So, and it is also important to mention that the original Capsule model is a flat classification approach and do not have a hierarchical structure, but it does share the capsule structure and routing process with our model. So here are the figures showing the model accuracy on MNIST and Fashion MNIST dataset as a function of training epoch for all the models under consideration. For MNIST dataset, all the models' performance are close to each other as it is a simple dataset. The difference in model performance are more apparent in Fashion MNIST dataset. And please note that for all the cases, our proposed model not just yielded higher accuracy, but it also converges much faster. Similarly, the figure presented here shows the model accuracy on CIFAR 10 and CIFAR 100 dataset. And for both datasets consist of more complex features compared to the previous datasets. Here, the difference in model performance is more clear. Similar to the previous result for all the scenarios, our proposed multi-level capsule network model performed better than other approaches, and compared with the baseline capsule network model, our proposed model improved a lot. And further, for model predictive analysis, we have considered a level-wise metrics and hierarchical metrics. So level-wise metrics overlook the taxonomical relationship among the levels. So we have shown the level-wise accuracy, precision, recall, and F1 score for all the models. So in order to do so, we have used a confusion matrix for the corresponding hierarchical levels. And the figure presented here represent the confusion matrix for our proposed multi-level capsule network on Fashion MNIST dataset. And further, we have performed the hierarchical matrices for all the models, which considers the taxonomical relationship between the levels. So here I present the level-wise matrices for all the models under consideration. The column chart on top represent the model accuracy per level. As we can see from the chart, for all the scenarios, our proposed multi-level capsule network yielded higher overall accuracy. The difference in model accuracy is much greater for complex dataset with larger number of classes in it. The column chart on the bottom represent the level-wise precision, recall, and F1 score. For a branch convolutional neural network and multi-level capsule network model, the first two bars represent the MNIST dataset. The next three bars represent Fashion MNIST dataset, followed by CIFAR 10 and CIFAR 100 dataset. For capsule network original flat classification model, it only shows the fine levels for all the datasets as it is a flat classifier. As we can see from the chart, in almost all the cases, our proposed network performed better than the alternatives. So similarly, here I present the hierarchical matrices for all the models under consideration. Hierarchical precision and recall are calculated utilizing the augmented sets of predicted and true values. The augmented set considered the taxonomical relationship between the hierarchies, where the hierarchical F1 score is the harmonic mean of the precision and recall value. As we can see from the chart presented on the top, for all the scenarios, our proposed model yielded higher hierarchical matrices, and compared to the baseline, it is much higher. Exact match measures the percentage of prediction that match exactly the ground truth for all the levels. For the exact match column chart, it is clear that our proposed model yielded much higher compared to the alternatives. And lastly, consistency estimates the proportion of the text examples that are consistent with the hierarchical structure, regardless the ground truth. So for flat classification, like baseline capsule network model, it will always be 100%. But compared with BCNN approach and our multi-level classification approach, which uses a taxonomical structure, our proposed network is much more consistent. And here is a sample reconstructed image for fashion amnesty data set. So from top to bottom rows, it shows the input image. The image was reconstructed by our proposed multi-level capsule network and reconstructed using the capsule network as originally proposed. So it is clear from the reconstruction samples that those reconstructed by our proposed model are much sharper and contains higher, better detailed. And this is somewhat expected since our reconstruction loss was utilized while training our model. So in conclusion, I would like to summarize that the capsule network for hierarchical classification has some advantages over the traditional ones, as it uses dedicated capsule layers per hierarchical levels. Also, our proposed model keeps a balance between the levels by employing a loss function, and which results in consistency among the levels. And finally, the proposed model improved compared to the existing ones. And thank you everyone for listening. For more information, you can reach me by my email. And if you have any questions, please feel free to ask.
Thank you very much for your presentation. Any questions, please? No questions. All right. We can continue then. Thank you. Okay, the next presentation is entitled Monte Carlo Dropout for Uncertain Analysis and ECG Trace Image Classification. The talk is going to be given by Farhadul, Mr. Farhadul Islam. It's going to be remote, yes, online.
Good morning, everyone. I'm Farhadul Islam, who will be presenting the paper titled Monte Carlo Dropout for Uncertainty Analysis and ECG Trace Image Classification. So let's start our presentation, introducing the problem and our goal of the study. So in 2019, the American Heart Association announced that cardiovascular diseases are the major cause of death. It accumulated over 17.6 million deaths in 2016, and the number is estimated to reach 23.6 million by 2030. But a patient suffering from myocardial infarction has a greater chance of recovery the sooner the abnormal cardiac activity is detected by an ECG. An automated ECG diagnostic system using deep learning holds the capability to examine the general populace and provide a valuable second opinion for healthcare practitioners. Now, we all know that deep learning has been successful in medical diagnosis, but deep neural networks cannot measure the uncertainty of its predictions. And obviously, uncertain predictions can lead to severe problems in the medical diagnosis. So for reducing the risk factors such as such issue in cardiovascular disease diagnosis using ECG trace images, we propose a Monte Carlo dropout-based convolutional neural network model. So in our work, we classify 5 distinct categories of ECG images, including COVID-19. We use Monte Carlo dropout to analyze the uncertainty of the model and find the uncertain sample for safer diagnosis. Now, I'll be talking about the related works in ECG classification, then uncertainty analysis in medical image diagnosis. So in most of the ECG classification studies, the input is either one-dimensional numerical ECG signal values or a two-dimensional image. So one work proposed attention-based 3-dimensional CNN model with residual connection, and another one developed 5 distinct deep learning models, and the prediction predictions of 3 machine learning classifiers is merged using a classification system, which is developing the implementation of a feature selection approach. And that model achieves 91.7% accuracy in 3-class classification. Now, in uncertainty estimation, studies regarding uncertainty in deep neural network prototypes are conducted in order to increase the reliability of the prediction methods. Evaluation of uncertainty in medical applications has been frequently applied for diagnosis of diseases such as COVID-19, tuberculosis, and cancer, etc. So one work used drop weights-based Bayesian neural networks to quantify uncertainty in deep learning techniques. They show that the predictive accuracy of the model was notably associated with its uncertainty. Another work implements shallow convolutional neural network model and with an ensemble model to classify motor imagery. Besides, they use Monte Carlo dropout to find the uncertainty of their predictions, which make their model more reliable. Now, let's talk about our methodology. We'll discuss about the data set we have utilized, the convolutional neural network architecture, and Monte Carlo dropout. In our study, we focused on developing a lightweight model with reliable diagnosis architecture. So the data set we use, the ECG images data set of cardiac and COVID-19 patients, which has 1,937 distinct patient records. And the data is gathered using ECG device Eden Series 3 placed in different health institutes across Pakistan. The data set is a 12-lead based standard ECG images for different patients with 5 labels, such as COVID-19, abnormal heartbeat, myocardial infarction, previous history of myocardial infarction, and normal. And the majority of cardiac abnormalities cause only slight variations in the ECG data, such as peak-to-peak interval or a particular weight. These differences are frequently used to categorize abnormalities. Here you can see the samples of the data. Now, data processing, we have pre-processed ECG images from the dataset by converting them from RGB to grayscale images and resizing them to 70 pixel resolution. We use the cropped version of this dataset where the images are cropped according to the ECG leads. This requires less computation cost and better classification performance as it enables the model to detect the abnormalities in the ECG signal. Now, the CNN architecture. In our model, we use 6 two-dimensional convolutional layers with 3 into 3 kernel size. And to avoid overfitting in the model, we added batch normalization layer after each convolutional layer. Batch normalization is used so that we can use a higher learning rate, as it allows every layer of the network to do learning more independently. Besides that, we use a max pooling layer after each batch normalization layer with a pool size of 2 to 2 to reduce the computational cost. And as the activation function, we use ReLU, as the non-saturation of its gradient accelerates the convergence of stochastic gradient descent compared to sigmoid tanh function. And we flatten the values to a single dimension, and we use 20% dropout from that layer. And the dropout is also used as the Monte Carlo dropout layer. And although batch normalization and dropout are regularization techniques, each of them have different tasks as well, other than regularization. During training, dropout modifies the standard deviation of the distribution, whereas it has no effect on the distribution during validation. Unlike dropout, batch normalization does not do the same. So we use softmax activation function as it is added at the end of the output, since here all the nodes are classified and our model consists of only 488,000 parameters, making it a very lightweight model. And here you can see the visual representation of our model. Now let's talk about Monte Carlo dropout. We all know that dropout decreases the model complexity and it helps to prevent overfitting, but it can be used as an approximation of probabilistic Bayesian models in deep Gaussian processes. And Basically, Monte Carlo dropout is a technique of performing numerous stochastic forward passes in a neural network using an activated dropout throughout the testing phase to generate an ensemble of predictions that may reflect uncertainty estimations. So if we are given a trained neural network model with dropout F, and to derive uncertainty from one sample X, we collect the predictions of T inferences with different dropout masks. Here, F presents the model with dropout mask DI. So we obtain a sample of the possible model output as the for sample X as in the equation you're seeing in the screen. Now, how do we obtain uncertainty? We obtain an ensemble prediction by computing the mean and the variance of this sample. The prediction is the mean of the model's posterior distribution for this sample and the estimated uncertainty of the model regarding X. We do not alter the dropout neural network model itself, but simply collect the results of stochastic forward passes from the model. This is done in order to assess the prognostic mean and uncertainty of the model. Consequently, this data can be implemented with the existing neural network model trained with dropout. Now, the experiments we've conducted for our study. The model has been trained and tested with grayscale images. Converting colored images from the dataset into grayscale images reduce the size or the number of unnecessary features of the images. And the images are randomly divided into 1:1:1 training, validation, and test datasets, which also maintains the ratio of the disease and non-disease classes in every subdataset. After an in-depth experiment, we use 32 training samples per iteration and set the epochs value to 70. We set the learning rate to 0.0001 because of using batch normalization layers. This learning rate gave us optimal results. Now we can see our results in this study. So we achieved the accuracy of almost 94%, and the same goes for precision, sensitivity of 93%, and almost all the results we achieved are better than the existing models. And the one noticeable thing here is we also conducted our experiment using the highest number of classes. Now let's talk about the uncertainty analysis. In the left, you can see the distributions of the Monte Carlo prediction accuracies and prediction accuracy of the ensemble in red. And the right, you can see four images actually. And in the first row, the model is predicting class 1 with very good confidence. But in the second row, we can see that the model isn't very certain about its predictions because the class 0 and class 3 are giving the same level of softmax score. So in this way, we separate the uncertain samples and leave it for the experts. Now, let's conclude and talk about our future work. Of course, as we showed, the proposed model makes the computer-aided diagnostic model more reliable and a more key. And another important part, which is it keeps the model structured the same as before and adds minimal cost to the inference time. And besides trace images, the growing popularity of smartwatches allows another bright idea to be explored, which is using a Monte Carlo dropout model in smartwatches, which are embedded with ECG trackers. And this will allow smartwatches to provide more reliable and real-time predictions. And smartwatches can inform the experts for dealing with the uncertain predictions, since many smartwatches have calling or messaging feature. So that's all from me. Thank you for your time.
Entitled One Against All Half-Plane Dichotomies, presented by Professor Nagy.
Bon, je voudrais remercier les gentils organisateurs pour encore une belle journée de travail. I'm going to talk about highly unbalanced classification. The first two papers were about many, many classes. I have only two classes. Just a little bit of terminology. Half plane means that it's linear, so in 2 dimensions it's a line. In higher dimensions, it's a hyperplane. A plane dichotomy divides some patterns of one class from some patterns of the other class. And one against all half-plane dichotomy divides one pattern from all the others. A homogeneous dichotomy has the hyperline or hyperplane through the origin. And a unitomy has all of the patterns on one side. And of course, you can convert these from one to the other. You can flip this pattern to the other side, it becomes a unitomy. And a unitomy is about the easiest kind of classification to do. I will give you a little bit of a summary in case I don't get to finish. We have the only data we have is an array of M entries or objects or restaurants or scientists or food with N attributes or features. The question is, how many of these rows can be separated from all the other rows? And it turns out that surprisingly many of them can be separated from all the others, far more on ordinary many-to-many classifications. The limit is used as shown 50 years ago is 2 times the dimensionality, and here we have far more. Each dichotomy separates, visualize it, a vertex of the convex hull of all the points, we'll see a picture, from all the other points. We know that the volume of a thin shell near the enclosing hypersphere grows rapidly to take over all space as the dimensionality increases. Most vectors in the points, and that's most all points, are linearly separable from all the other points. I will show that pairwise attribute difference vectors are useful for this kind of classification. And that weight vectors for unitomies, which are homogeneous, are easier to find than for the original weight vectors. I'll show some experiments with linear programming, and maybe you can do this kind of linear separation either with linear programming or with a single layer neural network, sometimes called a perceptron. And it turns out the same problem, the same solution applies to me first ranking any one of the rows above all the others. So here is a small example where n is 7 and n is 3, and look at the 5th row. We select, we find a weight vector, we'll see how, and that weight vector is 0, 1, 1, 1. If we take 0, 1, 1, 1 and multiply it by this, and multiply it by this, and multiply it by this, we get these values. So, for example, 1 88 times 0.11 is 16, and that is the highest value here, so we can separate it from the rest. And with these weight vectors, the highest value is always on the diagonal. If the usual algebraic statement is AW is given a threshold which says how far the hyperplane is from the origin, and is bigger than all the other products. This shows that all the vertices of the convex hull are separable from all the other points. You can imagine the other separating lines easily enough. This is a set of 7 points which are all separable from each other in 2 dimensions. This is a set of 4 such separable points, each with a different symbol, and each of these seven point sets are separable from all the others. So just look at it a minute. The interesting thing is that even in 2 dimensions, most of these points are in an annulus. It's not very thin. We are only talking about 2 dimensions. High dimensions don't apply here, but it suggests that as the dimensionality increases, the points will be concentrated in the thin shell. The little digression, what are pairwise difference vectors? Well, they are just the differences of the rows. This minus this, or this minus this, this minus this minus this, and so on. And so the difference vector is just the difference vector, and we can convert the statement of linear separability to a difference, to a unitomy. And it turns out that that is the same as the linear constraints for linear separability. Here is an image of linear separability of a set of vectors. This one, 1 against all, this is clearly separable from all these other points using, for example, using this weight vector and this hyperplane. So here it is again. We look now at the difference vectors, but in order to show a vector, we have to move them to the origin, and we see that it's a unitomy. All of these points are on one side of a line or hyperplane, all the pairwise vectors. So it's what the geometric statement of what I showed algebraically before. In high dimensions, all the points are in a thin shell in a hyperplane. And I think you can tell that any number of points on or near enough to a circle can be separated from the others. Now, in high dimensions, the shell makes up most of the volume, and this is what accounts for the prodigious separability, which I'll show you, of one against all separability of points in not very high dimensions, say 10 or 12. This graph shows how the volume of a thin shell, this one is 10% of the radius of the hypersphere, increases towards the whole volume of the sphere as the dimensionality increases from 1 to 19 on this graph. You saw earlier that points on the circle or near enough to the circle are separable. How near is near enough? Suppose that there are already 4 equispaced points on the sphere. Where can we put a new point somewhere in the same in the sector between these two that is still separable? And I think you can visualize that any point outside this blue region will either not be separable from the others or cause one of the previous points not to be separable. So we can only put them here. If the points were closer to each other, perhaps there are many more points already, then this blue area becomes smaller, but it never vanishes. You can always add more points. Okay, that completes the theory. This shows I'm going to show you pictures for different dimensions, 2 dimensions. It looks like as the number of patterns increases, the number of one against all separables reaches an asymptote, but it doesn't. Keeps on going up. Notice that up to about 5 is linear, and it's almost linear to 10, 20, and then it bends. Same picture, 5 dimensions. Up to m equal to at m equal to 10,000, about 10% of them are separable. Again, it starts out linear and then it bends. It keeps on bending. This is the number of one against all separable points. It's clear from geometry that in n dimensions, n plus 1 points are always separable. Think of a triangle or a tetrahedron, always separable. So here is n equals 12 dimensions, and it looks linear up to 500. 500 points are always separable. 1,000 points, about 900 are separable. At 6,500, 5,016 points are separable. What are these points? These points are just integer arrays pseudo-randomly generated in general position, independently pseudo-randomly generated in general position. There are, you can think of points that are not separable if they are coincident, for instance, or coplanar. So we are talking about points in general positions. What about n? Given a fixed number m, here is 500, and the integers have a range from 1 to 1,000. If they were only ranging from 1 to 4, that would be too many coincidences. But at 1 to 1,000 in 12 dimensions, coincidences, collinearities are very rare. So if you have enough dimensions, in, it looks like 11 or 12, all 500 points become separable. If you had 10,000 points, you would need 20 or 22 dimensions until they are all separable. The more points you want to separate, but the dimensionality rises very slowly with the number of points. This is, we are not really interested in computational speed, but we did compare linear programming and an alpha perceptron, which I programmed myself because the available feed-forward networks from the packages had too many hidden parameters, and I was not able to control all of them. But in any case, the fast on either 2 dimensions or 12 dimensions, the linear programming is fast, and working on pairwise attribute vectors is much faster than working on the original attribute vectors. Why? Well, we don't know, but differences seem to be magic. The derivatives appear in all optimization problems. It looks like the difference vectors are more independent on real data than these vectors. But unfortunately, we don't see how to extend them to balanced dichotomies because there are an exponential number of difference vectors. Why is training a neural network so much faster for one against classification? We believe that it's because every with difference vectors, every pattern affects the weight in each epoch, whereas in one against all, this designated pattern would only affect the weight one against all in ordinary classification. Last slide. If you can separate a pattern linearly from all the other patterns, that means that you project it on a weight vector, it will have a higher value than the projection of all the other values. So it's clearly a ranking. So me first ranking and one against all half plane dichotomies are equivalent. And that's what I was talking about at ICPR. Thank you.
Thanks very much. Any questions?
You know, there is a, if you, for example, have a few-dimensional space and it's non-linear separable, it's known that if you apply kernels to go to the higher dimensional space that can be separable. That's basically what Vladimir Wagner states.
You mean like support for machines?
Yeah. So you go to the higher dimensional space, it's also linear,
yes.
But in the fewer dimensional space, it's not separable, and then it's separable.
Yes, that's for balanced dichotomies.
Yeah, but there exists the minimal? Is it possible to define the minimal dimensional space where it's linearly separable?
An infinite number of points are separable in 2 dimensions, one against all. An infinite number of distinct points on a circle or even a circular arc are one against all separable. Put the points very close. There is a hyperplane at each, just below the tangent hyperplane. An infinite number as long as there are no coincidences or collinearities. If you go to, instead of one against all separability, consider 2 against all separability, then every adjacent pair is linearly separable from the rest. If you have 3, then every 3 against all, adjacency against, by the number of 3 adjacent 3 points on the circle is a very small fraction of the total number of 3 chosen points on the circle. So you don't have to go to any higher dimension if you can pick your data. The reason why we go to higher dimension is because if you just pick point, they won't all be on the circle. But as the dimensionality goes up, they will all be very close to the hypersphere, because that's the whole volume of the space is very near the hypersphere.
So basically, this is the guarantee. If you go to the high dimensional space, they will be all linearly separable. There is a guarantee that if you go to the higher dimensional space, they will be all this.
There is a guarantee as long as there are no coincidences, collinearities, coplanarities, and can anybody help me? What is the next word? I can't think of what is above coplanarity or co something, but
co-quadraticity or co-quadraticity,
something like that. Yeah, that's all I'm saying.
Okay, so let's end here. Thank you again.
Good morning, everybody. I'm Nagy, PhD student of Vienna University of Technology, and my supervisor is Professor Walter. So today I talk about our paper, fast distance transform in graph and in Gmax. So what is the Okay, what is the distance transform? So distance transform actually computes for every pixel of the image, the pixel of the 3D image, how far is from the closest obstacle or boundary for the background. So in topological structure, like graphs, combinatorial maps, or generalized map, it actually computes the shortest path between the obstacles and a given point. So the goal of this paper, which actually the three main contribution of this paper is first, we compute the distance transform in a graph as a non-grid structure. Then we define distance transform in a generalized map. And finally, and most important, we compute the distance transform with parallel logarithmic complexity, lower complexity than linear distance transform. Note that the parallel complexity means that we use parallel architecture that actually we assume that we have sufficient processing elements that they work together simultaneously. So let us start with the graph. So in computing the distance transform, we need to have some seeds to propagate the distance from there. To this end, we do the age classification. In a binary, we have the gray value 0 or 1, the 0 for background and 1 for foreground. So in the binary graph, we have two contrasts of the edges because we have two values. So 0 edges and 1 edges. So the 1 edges actually plays the role of these seeds. So in the 1 edges, the points from the background receive the 0 value and from the foreground 1 value. This is the initialization over the binary graph. So then for doing the parallel processing, actually we need the independent processes or the set of independent edges here. So we use total over the vertices. Actually, each vertex of the graph we assign a unique vertex to that. So the property of the total order is that any two elements by this, they are comparable. And the nice property is that every subset of vertices has only one maximum and one. So then for every vertex of the foreground, we search in its neighborhood and we find the maximum value around that. So by this, we create the spanning forest of the foreground only in one parallel step. And then we can propagate the distances over this foreground forest, spanning forest, and we can propagate the distances in the order delta, where the delta is the maximum diameter of the object of the foreground. Or we can do like the maximum independent edge set and we propagate it even in lower complexity, like logarithmic ones. Next, I go to the Gmaps. The Gmaps or the generalized maps are a combinatorial structure that they can allow you to describe orientable or non-orientable Kusy manifolds. The fundamental elements in the Gmaps are dots. Dots are half-edge. So more precisely, n-dimensional generalized map actually consists of n+2 tuple. So we have a set of dots and n+1 involutions. And for example, in two-dimensional G-map, we have a set of darts and alpha 0, alpha 1, and alpha 2. So actually, these involutions are responsible for propagating the distance through the G-maps. So in G-maps, we initialize the points actually here by darts. So we have, for example, here a dart seed by 0, and then we can propagate in every involution like this. So to see what happened to compute or to define the distance transform over the G-maps, if you see here a binary example, a binary 4x5 image, that we have 3 pixels of background and the remaining vertices pixels as a foreground. So if we compute the distance transform, we have the output image by 3 distances. But if we use this over the G-map, we have like 10 different distances here. So it means that the output image actually has a high resolution or finer or smoother distance transform. Now I go to the one special case or important case of distance transform, that is geodesic distance transform. Geodesic distance transform actually used for labeled images. And we have interest of a component as a foreground and the remaining as a background. So for example, here you see a slice of the leaf that we have 6 different labels. Like we have cells as a green, we have airspace inside the leaf as a gray, and we have stomata, as these 3, as a magenta color. Yeah. So actually, biologists are interested to know how photosynthesis takes place. So the stomata works as a gate. So they open and the CO2 entering the airspace that reach to the cells, and there, by combining with the water and heat, the photosynthesis takes place. So we use distance transform actually to compute the diffusion of the CO2 inside the airspace. Essentially, this is currently we are working in a project named Water's Gateway to Heaven with the biologists from Boko University and the University of Vienna. We wanted to simulate how these stomata open or close to do the photosynthesis in the leaf. But here, the 3D image that we use is big images, more than 2,000 by 2,000 by 2,000 each size. So it means that we have a cubic image more than 8 billion pixels or voxels. So if we wanted to do the common distance transform, linear distance transform, it is very time consuming. That's why we offer the hierarchical structure. The hierarchical structure or pyramid consists of series of successively smaller images that produce from the base. So in the pyramid, we can do parallel processing, and we can build the pyramid only in log step, and the log of the image size. So there we can propagate the distances in logarithmic. So the main idea is that propagating the distances are a set of power of 2. So you here see, that we have a one-dimensional array between 1 to 16, and assume that we want to propagate the distance from this most left to the 16. In linear, we need to propagate the step, 1 by 1. It takes 16 steps. But if we do it with the connected hierarchical structure, we only need 4 steps. So assume these 8 billion pixels, by using this hierarchical structure, it only needs 30 steps. And this is a very big advantage that we can compute the distance transform in a very fast way. So to see the that how we use the hierarchical structure, this is a general image of the pyramid, that we have a base level, top level, and then we have base level. So we have two fashion of propagations. We can propagate from bottom to top, and then from top to down, or top to bottom. So the base level of the pyramid, the important thing is that we select independent edges or kernels, let's say, contraction kernels, that we can reduce the number of vertices and edges. So to do this, actually, we also offer logarithmic encoding, that how we can choose this independent set of edges. Then by contracting them, we reach to the smaller graph at the second level, and we preserve the number of contractions for each surviving actual edge to preserve this history. So then we can continue and go to the next level until we reach the top of the pyramid. Then every surviving vertex has its own distance transfer. Here, we now propagate down. And actually, every surviving vertex, as like further, propagate this distance into its stars. And by this, we can reach to the, again, base of the pyramid, where all the vertices has their own distance transfer. So, as a summary or conclusion of my work, we have computing the distance transform in graph. We did edge classification, use total order, and we computed a spanning forest of the foreground only in constant parallel complexity. We defined a new actually distance transform on a generalized map that provide us finer distance transform. We compute the geodesic distance transform with parallel complexity, and for the application, actually we use it for the simulation of the gas exchange between the stomata and the cells in the leaf. So these are the reference, and thank you for your attention. Thank you.
Any questions or comments? You are forbidden to ask questions.
So I just can say something about the first slide.
Okay.
That's this is a temple in Iran, in the Asian of Iran, called Ziggurat, Chogha-Zanbil, south of the Iran. And actually, it's the smallest version of the pyramid, very simplest version of the pyramid. So I use it here because the hierarchical structure of the pyramid that I use actually is simpler than the big pyramid of the Egypt. Okay. So,
okay. Titled Retargeted Regression Methods for Multi-Label Learning, given by Carlo.
Hello everyone, I'm Kimura from Hokkaido University. Our paper title is the Retargeted Regression Methods for Multi-Label Learning. This is a collaboration with Jackie Bao. She's a PhD student at Hokkaido University, and Professor Mehedi is sitting there and waiting for his presentation turn. And Ruslan from the Professor Ruslan is from the Syntactic University. Okay, so in this paper, what we want to solve is multi-label classification. That is a classification problem that allows the instance have more than one labels at once. I think it's not necessary to explain for you, but this is here's the example. This is a beautiful picture of the Montreal city. We can give the labels of the sky and building and river at the same time. So in some cases, this multi-label classification is a natural setting. So the more formally said, we want to find the relationship between the F-dimensional future vector and the L-dimensional label vector, and predict the from the future and the labels. So the key idea to tackle the multi-label classification is how to model and how to utilize the label relationship that appears in the label matrix here. In the traditional single label multi-class classification, each instance has only one label, so the label relationship is hard to obtain. But in the multi-label classification, we can observe the co-occurrence of labels. I would like to introduce two conventional methods to model the label relationships. The one is the classifier chain. They first construct a DAG of labels and then prediction result of the parent labels used as the future. This is an example. First, where we in CC that it constructs a binary classifier, binary classifier for the L1. Then just predict and obtain the prediction results of Y1. Then it constructs the L2, and for L2, L2 has a L1 as a parent, so they use the prediction result as a future. So they construct a binary classifier for L2 with X and Y1, and predict the Y2. And L3 is also like doing them as well. So they can directly model the label relationship with the DAG of labels. The other one is a label space dimensional reduction. They first decompose the labeled matrix into the low-rank matrices as well, and like this. Then learn regression to low-rank matrix, not to run the regression to the label matrix. Then we can obtain the low-rank vector with this regression matrix for each instance. We can use this matrix B for the decoding matrix to obtain the L-dimensional prediction results. So this level space dimension reduction methods models the label relationships through the low-rank structure in the label matrix. But in the level space dimension reduction, unfortunately the low-rank assumption for the label matrix that is had the low-rank structure is very huge, and unfortunately it's not hold in the real data set. And the classifier chain also has a drawback that we cannot, it implicitly assumes that there's a structure in the DAG in the labels. So in this paper, we want to model a new model to utilize the label relationship, and we extend the retargeted least square regression to achieve this. So let me introduce this method first. This method is originally proposed by Sun and for the multi-class single label multi-class classification. The key idea is not only learning the regression matrix, but also the modifying the target matrix. As you can see that here, maybe I should use this next month. Here in the original regression, we should use the label matrix for the target here. But instead of that, in this method, we use the matrix T, and this is also optimized. we want to solve the multi-class classification, so we have to guarantee the classification accuracy. So they are the subject, and here that means the correct class, the target value of the correct class is always larger than the incorrect class. Since in the multi-class classification, we use the class decision rule, that is we assign a class that got the highest score in the regression. So if we use if we satisfy this constraint, the multi-class classification will be succeeded. So that means if the correct class has the target, the largest score, it will be classified correctly, whatever its score is. So now it's not necessary to regression for the 0-1 matrix, but we can modify the target matrix. So our proposal is very simple. It's an extremely simple and natural extension of that. We extend the targeted least square regression to the multi-level classification. You can see the difference is just here. In the multi-class classification, they ask the correct class has the highest score, higher target. But here we ask all positive labels have the larger target than those of negative labels. So we also introduced the hyperparameter design for this constraint. I will explain later. But I would like to say that this is not a struct variable. I think that many people can see that this looks like a margin constraint in the sample vector machine, but it's not. Actually, this method does not maximize margin, but this method asks the fixed wise margin between positive labels and negative labels. So this retargeting mechanism brings a label to label interaction, because this constraint is actually for the instance wisely. I moves to the 1 to n. So those target values directly affected each other. So we think that this brings a higher accuracy and utilizing the label relationships. Okay, optimization for the REML solve is very simple. We use the alternating optimization approach. We update the regression matrix W while fixing the target matrix T, and then we optimize the target matrix T with fixing the regression matrix W, and we conduct those iteratively until convergence. So to run the regression matrix W, it's not necessary to modify the optimization for the regression. So we are using the linked regression for that. So the optimal solution is this. But the optimization for the target matrix has a little bit complicated. So I would like to explain that. So let me use the score matrix R, because the regression matrix W is fixed, and we also use the low vector of the target matrix, and I would like to call the target vector, and the score matrix score vector is also the low vector of the score matrix. So the reason why we use the low vector is we can decompose that problem into low wise ones like this. It just decomposed, and we picked up the ice low vectors. I mean ice instances. So we have to care there's still the constraint, and there's a minimum operator and the max operator. So we have to care about all pairs of positive and negative labels. But actually, it's simply solved just introducing the midpoint of margin alpha. So the problem, actually the problem is just where should we insert the margin, because the margin is fixed. So the y is 1 minus xi. So if we once we set the margin, where the margin, then we all of the various target vector will be calculated. For example, the positive labels, if we set alpha is here, that is the midpoint of the margin, and then the target and of the positive labels. If the positive labels, the score of the positive labels is larger than the margin, then it's okay. It's not violated constraint. So the optimal target will be the score. But if it's below the margin, the target must be the top of the margin, because it's to satisfy the constraint. Negative labels is also like that. So the optimization problem is actually where should we insert the margin in a midpoint of alpha. So we just solve this problem. That is a square hinge loss. And this objective function is related to the ranking of labels. In traditional method, such as binary, because I haven't explained, but that is construct a binary classifier for each labels and combine it. It solves the label-wise problem. For each label, they construct the classifiers like this. So ignore the relationship between the other labels. On the other hand, our method is considering the labels. Because we are caring about the order of the labels for each instances. This is a major difference between the traditional method and our method. Okay, but I haven't explained the drawback of our method. That is a threshold of the 0-1 to obtain the 0-1 classification results. Since the target value of the regression is modified for each instances, so we cannot use a constant threshold to obtain the 0-1 classification. For example, simple regression, we can use the 0.5 to obtain 0-1 classification results. But now it's modified, so we don't know how much it is. So we propose a simple heuristics to estimate the threshold for each instances. That is k-nearest neighbor. We find the k-nearest neighbor from the training data set, and then average of the midpoint of margin alpha. That is the ideal threshold value for each training data set. So we use around alpha for that. After that, we use the threshold to obtain the 0-1 classification like that. Okay, that's all the proposal method. And here's the experiments. We conducted the experiments on the 9 data set. And we compared with the binary relevance. That is the simplest method for the multi-label classification. And the second one is a CPRST. That is one of the label space dimension reduction method. The third one is a classified chain I already explained. The fourth one is a proposal. Okay. This is a result of the RCAC. Actually, the instance-wise RCAC, we calculated for each instance and the average of them. RCAC is known as a ranking metric, and this is a result. All cases, the best cases. As you can see, our proposal performed the best in the 6 out of 9 data set. This is a natural observation for me, because we are this method are caring about the ranking of labels for each instances. So this is natural to get the highest score. And this method shows significant improvements on relatively larger dataset, BFTech and 405K, those are larger datasets in our benchmark dataset. And this result shows the RS map could run the correct orders of scores by utilizing regular relationships. This one is the 0-1 classification performances. Unfortunately, it's hard to. I couldn't find the significant good insight from that, but I can say that the proposal heuristics works well enough. Indeed, the proposed method performs better in the respect of the macro F1 and the micro F1 and the score. So it's not difficult to determine the threshold without heuristics. There's parameter sensitivity analysis, but I think I should skip because it's time. So here the conclusion: we extended the retargeted least square regression to the multi-label classification that has all positive labels versus all negative labels constraint. We also proposed the simple heuristics to our 0-1 prediction. We conducted experiments on 9 benchmark dataset, and they show the best performance in an instance-wise ranking metric, and it showed a significant improvement in some cases. And simple heuristic works well, and there are future work at the time. So that's all. Thank you for listening.
Distinguished experts, teachers, and students, good morning. My name is Sun Xiaohu from Nantong University. I'm honored and proud to have the opportunity to speak at this meeting. Today, I would like to present my paper, Transformer with Spatial Temporal Representation for Video Anomaly Detection. My presentation will cover the following aspects: background, related work, methods, experimental results, and conclusions. With the popularity of smart surveillance devices and the increase of people's security awareness, video anomaly detection has become an important task. However, learning rich multi-scale spatial temporal information from high-dimensional videos to predict anomalous behaviors is a challenging task due to the large logical redundancy and the complex global dependencies among video frames. Currently, video anomaly detection methods are divided into two categories: reconstruction-based methods and the prediction-based methods. Among them, reconstruction-based methods assume that models learned only on normal data cannot accurately reconstruct anomalies, and thus anomalous samples will have large reconstruction errors based on this distribution. Unlike the reconstruction-based methods, the prediction-based methods focus on the prediction of the next frame by using the content of the previous frame and the current frame. Transformer was first proposed for solving NLP tasks. In recent years, Transformer has demonstrated powerful modeling capabilities for sequential data, and there has been a lot of work applying Transformer to the field of computer vision. For example, image classification, semantic segmentation, object detection, etc. However, it is rarely used in the field of video anomaly detection. Learning rich multi-scale spatial temporal information from high-dimensional videos to predict anomalous behaviors is a challenging task due to the large local redundancy. At present, there are mainly the following problems. Firstly, CNN has extraordinary bias induction capabilities. The inherent localization limitations lead to their lack of ability to capture long-term spatial temporal features. Secondly, Transformer has the ability to capture global information, but lacks the ability to bias induction of local features. Therefore, we propose a transformer with spatial temporal representation for video anomaly detection, as shown in Figure 5. This network combines the transformer mechanism with convolution in the encoding part, which retains the bias induction ability of convolution and introduces the powerful modeling ability of transformer in long-time series, and achieve better global feature learning using the self-attentive mechanism. Specifically, in order to preserve the shape and other features of the image, we perform convolutional coding before transformer coding. After each convolution, the maximum polling operation is used to reduce the feature map size by 2 times. Then we reshape the feature maps without overlapping each other and vectorize the patches to a latent d-dimensional space using a trainable linear projection. To encode the patch space information, we embed the learned location-specific information into the patch embedding. The structure of transformer encoder is similar to that of NLP, which consists of MSA and MLP blocks. MSA as the core model in the transformer block uses a parallel approach to train multiple value vectors, and then stitch them together to get the output. To identify anomalies in the video, we provide a regularity score for each frame, with higher scores indicating a higher probability of normal. We train and test our model on 3 well-known video anomaly detection datasets, as shown in Figure 7. We mainly use AUC and EER to evaluate the performance of our method. To evaluate the effectiveness of our proposed method, we compare it with 8 different methods. From Table 1, we observe that for the temporal methods, our method outperforms standard LSTM and GRU. This is because our proposed model is a hybrid model combining transformer and CNN components, and the features extracted by transformer include not only contextual information, but also long-range global dependencies as well as inductive bias features of CNN, which makes it easier to discriminate the recognized objects in motion prediction. Although RNN-based anomaly detection methods are powerful and effective for temporal data processing, their potential for gradient disappearance or gradient explosion. In addition, our method achieves lower EER at frame level with 0.123, 0.220, and 0.319 on 3 datasets. As can be seen from Figure 8, the frame level ROC of our method on the 3 datasets is significantly better than the other methods. We also qualitatively analyzed the anomaly detection performance of our method on 3 datasets and visualized it as shown in Figure 9. In each subplot, a higher regularity score indicates a higher probability of normal. To evaluate the effectiveness of our method, we conducted ablation experiments on 3 datasets. It can be seen from Table 2 that after combining transformer with the unit, the AUC on the 3 datasets are improved. This indicates that our method can both preserve the detailed features of the image by convolution operation and preserve the global features of the image by using transformers' effective learning ability of contextual information. On the other hand, it also reflects that the limitations of the convolution operation limit the ability of the model to extract global features of the image. While combining the convolution operation with the transformer operation can better capture the spatial-temporal dynamics and thus allow for more accurate detection. At the same time, we found that the bolting effect on Shanghai tick is much higher than the other 2 datasets, which is because transformer is better at handling complex data, while the Shanghai tick dataset is more complex compared to the other 2 datasets. Figure 10 shows the comparison results of AUC for unit and unit plus transformer on the 3 datasets. Our transformer plus unit approach predicts higher AUC values compared to the traditional unit approach, which indicates that the combination of transformer and CNN has an advantage over other approaches in video dissimilarity prediction. Finally, I would like to make a conclusion with this presentation. The network combines the bias induction capability of CNN and the powerful self-attention mechanism of transformer for future frame prediction, which not only can effectively obtain global contextual information through the MSA of transformer, which not only can effectively obtain global contextual information through the MSA of transformer to compensate for the deficiency of convolutional operation in this aspect, but also can take advantage of the pyramidal structure of unit to make good use of the shadow CNN of future map features to achieve better results. In our future work, we will future explore how transformer and CNN can be more perfectly combined to achieve its more powerful application in the field of video anomaly detection. I'm honored to report and share my paper with you. Thank you very much for listening.
So we move on to the last presentation, entitled Efficiently Leave One Out Evaluation of Kernelized Image Mappings. It's going to be given by Professor Mehedi. So
I come here to share with you a finding, a simple finding. Okay, so that is a leave one out technique can be applied if we choose KIM. I will explain about that kernelized implicit mapping. So this way. Okay. Okay, let me start with background. As you know, many embeddings cannot handle new sample. So let me explain it by taking Laplacian IMAP an example. In this case, this is sorry. I'm good at this one. Where the eraser, don't be this one. Red one, yes. Okay, this is a feature space, and there are many there, and we want to embed these samples in lower dimensional embedding space. So in the first and eigenmap, we adjust the position of embedded vectors to minimize this equation. Since W means a similar is a kind of similarity between Xi and Xj, so the task is to do something like that. Closed pair should be also closed in embedded space. But unfortunately, we cannot handle new sum. So one solution is to use a linear like this A, but it is obviously restricted. So we propose another one that called is kernelized implicit mapping. Given a set of pairs, original and embedded vectors, we transform it with the linear combination of kernels associated with every training samples. This is our idea. This can be applied to any implicit mapping. And the form is supported by famous representative theorem. When we apply this way to all training samples, we have this equation here. And here G is called gram matrix. And fortunately, G can be embodied if we adopt an RBF kernel. So we can find an optimal correlation matrix like this. And putting this equation into here, we have the last result. And fortunately, we can prove this KIM can simulate perfectly the mapping over training samples. It can be proven very easy. Just K becomes gram matrix, then G inverse cancel it, and Z appears. That is proof. Once we determine to use KIM, the next question is, the natural question is how to what degree it has generalization ability. So we propose to use leave one out technique. So in this case, we first leave one sample out and embed all remaining sample here. And then we simulate this embedding by KIM. Come on, okay. Then KIM can apply to new sample. We map Xi to here. Oh, okay, here. And you already measure the difference between original and embedded sample here. This is our way. So our objective is like this. When some implicit map is simulated by a KIM, then we can show it leave one out technique can be applied very fast. Actually, this equation shows a naive way. In this formulation, we have to n times of calculation of inverse. It's very costly. But we will show it can be done by just a single multiplication of two matrices. The basic formula is very simple. As for the inverse of matrix for our partition matrix, we can have this formula. When we apply this formula to our gram matrix, we have like this formula, and comparing this one and this one, we notice we have already the solution inside the inverse of gram matrix. Almost we have the answer. Let me show an example. This is gram matrix, but the first sample is left out. Then this calculation can be calculated like this. But if we have the inverse of gram matrix, the things become very simple. what we have to do is just divide every element by the corresponding diagonal elements. In this case, we have this one. So this is almost the same to the answer. Only difference is a sign. In this case, in summary, what we have to do is just divide every element by the corresponding diagonal element and multiply -1. And once we set the diagonal elements to 0, that's all. Then we have LOO matrix. That is our finding. For the remaining, I will show some applications. First, we noticed LOO matrix is independent of Z. So by changing Z to what we want, we can have many applications with almost no additional cost. For example, for visualization, we can use two-dimensional data, two-dimensional vectors for Z. And classification, we can use one-hot vectors. And image construction, reconstruction, we can use image data itself. Okay, in this case, I will show some example for visualization first. Visualization is often used for parameter estimation or model selection. In this case, the first row shows different kernels, and second row shows the same kernel, but the different values of parameters. So from the error rate calculated by LOO matrix, the smallest one shows good results, and that is very close to original embedded samples. So it works. If we use one-hot vectors for class representation, we can confirm leave one out error estimation is quite good replacement of testing accuracy, and the performance is good. So this is the last one, the reconstruction of a single image from the other images. I will skip the detail. And also I did a simple analysis. This shows every element, in every column, the sum of values is close to 1, which means this LOO matrix is relative because we can change Z freely. Then we have to require the scale invariant. So sum to 1 means scale invariant. Here I have to confess. Unfortunately, this finding is not ours. Of course, we found it independently, but other researchers already found it in the special applications like kernel weight regression or least square kernel machines. But the difference is theirs is one-dimensional. Output is one-dimensional, but ours is multi-dimensional. So LOO evaluation is a little different. It can also show our way can be extended to affine transform by adding a constant term, and also can apply to usual cross-validation technique. So let me conclude. When some implicit mapping is simulated by KIM, then LOO evaluation can be made with almost no additional cost. Actually, what we have to do is scanning the inverse of gray matrix. The same LOO matrix is available for different goals: classification, visualization, and reconstruction. The problem is its high cost. Unfortunately, it is huge with respect to the number of samples. So we have to think something. Thank you.